Good evening, everyone. I am Bandhuka Kurupu, Technical Events Coordinator for Civil Engineering Sectional Committee. And this is the seventh session of our lecture series on structural design of highway bridges. Our sincere gratitude to Professor Tisanjaya Sinha for the commitment in giving this lecture series to uplift the knowledge of our practicing engineers. And for the issuance of participation certificate, I would like to request from you all to add your membership number as well, along with your name. Please rename like that. And if there are any new members, you can join our WhatsApp group for the study materials. We will share them again through the group. And over to you, sir.
Thank you. Thank you very much. Last time we introduced the fundamentals of prestressed concrete, and we actually derived these equations. And then at last, I told you that if you can select a section somewhere there, that means eccentricity is somewhere there, prestress is somewhere there, then we can go for a minimum prestress. Then you'll ask why minimum prestress? Because steel is very expensive, so we must go for minimum prestress. Baluka, can you hear me properly?
Yes, sir. Yes, we can hear you, sir.
So today we'll see how we can move forward. Now, if you look at a cross section, then a rectangular cross section versus one of I section having the same width and the same height. Now, if you are going to now if you look at these two sections, we can see self-weight. This one is higher, this one is low. Then area, this one is higher, this one is low. Now in pre-stress, we are looking at two effects. One is P over A. Other one is this compression, and we want compression here, tension here. So this is PE over Z2. This is PE over Z1, right? So we are at them. So if you want to maximize the pre-stress effect, then we must minimize area. We must minimize the area. So, which means this is rectangular section is less efficient, and this is more efficient. So that's one thing that you can gather from this diagram. So today's Civil Engineering Sectional Committee 4th 2023, and note page number 1. I'm numbering everything so that we can share the information, and you can follow it, follow the notes with the recording, right? So if we look at pre-stressed concrete, so what are the rules? Minimize the area. Number 2, allocate material as far away as possible from the neutral axis, or we call it centroid. So because in free stress concrete, because the field section is effective, centroid and neutral axis both are the same. So our rule is allocate material as far away as possible from the neutral axis. Then we know when you are stretching, initially it will deform like this. Initially, going to deform like this. Deform like this, because we have no load on it, only the weight of the beam. Weight. Then when you are using it, it's going to fail like this. So that means the strength is also important. The reason is when you are transferring, we allow the tension is, whatever the tension that you have decided to apply, and we say it's a maximum tension at transfer. And it's generally in the range of about 2 newtons per millimeter squared. Right? Generally 2 to 2.5 newtons per meter squared. But so generally it's in that range, right? And here the maximum strength is 0.6 times whatever the strength at transfer, whatever the concrete strength at transfer. Now, when it fails, it does not fail due to permanent loads. It fails due to the maximum load when we apply whatever the loads, maximum loads. So here we can have another tension at working load, which may be about 2.5 newtons per meter square. But if you want, you can go for higher values. But then you have to have some guideline on the, you have to deal with the crack, because beyond this, it's going to crack. So in Eurocode, it doesn't say you have to stop at 2.5. If you want, you can go for higher stressors and go for get a more efficient design. But if you think, durability is a great concern and you don't like any cracking, then you can maintain the tension around 2.5 newtons per millimeter square. So that is all your decision. But to understand this better, we'll assume that we are going to control the maximum. We are going to control the maximum. Right? That is too fast to understand what's going on. Right? So because we don't want to make things too complicated, so let's assume we are not going to have too much tension. We are going to control the tension. But the important thing is, now here you get 0.6 times FCK. So higher the stress, if the stress is, if you go for higher strength concrete, then you can actually go for a smaller section, because we are allowing higher stress in the section. So for that, now we have to think about the concrete strengths. So if you look at the concrete strengths that are available, so I can share the screen for a moment. So this is the note that we are using for other subjects. Here you can see the strength of concrete. So generally, if you go with the cube strength, when we do post tensioning, in the early days we used 30 megapascal concrete, and we did the transfer around when it reached about 22 or 25 megapascal, right? So we did the transfer around this. So we used 30 megapascal concrete when we had post tension beams, and we had about 40 megapascal, something in between, when we did pre-stressed concrete beams. The reason is pre-stressed concrete is done under factory conditions. So because of that reason, we can go for a higher strength, whereas post-tension concrete means the site mix concrete. And those days, I'm talking about something like 30-40 years ago. We did not have admixtures to the extent that we use it today. So because of that reason, 30 megapascal concrete was obtained by using cement. Whereas 40 megapascal concrete was also mainly using cement, and they did not go for any kind of admixtures generally. But if you want to, you can use. But because the admixtures are important these days, not manufactured in Sri Lanka. Because of that reason, we stayed somewhere around 40 megapascal. So then what happened was now we have a very different situation with concrete technology. So we have to see how we fit into today's scenario. And so you can see using 30 megapascal maybe little too low, and even for post tension beams, use of 45 megapascal may be a reasonable value. So we are talking about FCU of 45 megapascal, which gives FCK of 35 megapascal. Right, FCK of 35 megapascal. Right. So FCK is the cylinder strength, FCU is the cube strength. Right? So if you look at the tension values, here you get the tension values, yes. And if you are using that type of concrete, the tension values will be in the range of 2.2 newtons per millimeter square, the tension value. And you can also see the elastic modulus is about 30. And so if you want to even optimize further, you can go for something like 55-45, and then the elastic modulus will be 36, and you get a slightly little higher allowable stress here. But when you take 0.6 times 45, when you take 0.6 times 45, uh, 0.6 times 45, we end up with something like 27. The allowable stress is 27, sir. And then 27 plus, we have another about 2.2, 2.7. So we are allowing something stress range close to 30. It's a huge stress range for the stressors. And that means, you might be able to use a smaller section and, go for an economical design. So then the question comes, all right. So if the question comes, how are we going to manufacture this concrete under normal situations? So we'll just spend little time on this concrete technology, because there can be some last year also I explained this in great detail, but we'll spend little time just looking at the practical aspect. How are you going to get 35 megapascal cylinder strength or 45 megapascal tube strength? So we say, we are going to concentrate on this study. And because there are certain conditions that you have to meet when you are dealing with pre-stressed concrete. So in mix, you get cement, sand, aggregates, water, and then you get wet density. And so if you are looking for something like 45 megapascal concrete, so you have to at least use something like 500 kilograms of per meter cube of cement, because the equation is 45 multiplied by 10 plus 50. This is the kind of approximate guideline. So you just multiply the grade by 10 and add 50. Then the amount of water needed is 200. Wet density is 2500. These are fixed numbers. Here you get X and Y. And X to Y ratio, sorry, Y to X ratio can vary between 1.5 and 1.8, right? Again, we need a very neat finish. So we like to have some certain amount of sand. So we might limit the upper limit to about 1.8. And if you are going to go with 1.5, then you can say X plus Y is equal to 2500 minus 500 minus 200. That is 1800. And X is 1800 divided by 2.5, and 1800 divided by 2.5 1800 divided by 2.5 equals 720 kilograms per meter cube. And so the remaining part will be 1080 kilograms per meter cube, and this will be 750. So can straight away get this one. And if you look at the water cement ratio is equal to 200 divided by 500, which is equal to 0.4. Fairly low water cement ratio. It's a fairly low water cement ratio. But you are going to get 45 megapascal. And if you look at the kind of strength development curve, because we know so the main ingredient is C3S, C2S, C3A aluminate, tricalcium aluminate, tetracalcium aluminum ferrites, and here these about 50%, 25%, 8 to 10%, and this is an impurity that's about 10%. Today it's about 65 to 70%, 5 to 10%, 8 to 10%, and 10%. So if you look at the strength development curve, we'll get a very rapid development of the strength, and the chances are that after about 5 to 6 days, we'll get a strength that we can expect as 45 megapascal. You can get that. So which means This might reach a strength of about, so 45, so might reach a strength of about 35 in 3 to 4 days. So when you are doing this pre-stress concrete, you can see, we have to transfer the stressors before we move the beam, because beam has very little strength, so we have to transfer the stressors before we move the beam. So this number 2, the civil engineering sectional committee. Number 3, and today is 4th, 2020. So because the reason is we are going to use this one option is, we can cast the beam like this, where we are going to get curved tendon, and we use this for postage. The other option is we have tendons centroid lying here, and then we have the centroid lying elsewhere towards the end, and here we got debonding. We get debonding, and we make sure either this or this, and this is for pretension. We use this for pretension, we use this for post tension. So whatever it is, we are using steel shutters here, because we need finish. We generally use steel shutters. So steel shutters are very expensive, so we like to finish this operation as early as possible and remove the shutters and move the beams out away, so that we can start casting the next batch, right? So if you look at today's scenario, all this is possible because we are having cements that gain the strength very fast, but and also because we are going for, if you look at the earlier situation, we go for very small sections. Again, there's a minimum width that we can cast, something like 120 to 150 millimeters, because we can't reduce it anymore, and we get a section like this. So if you look at the section, then this is a penalty. This area is a penalty, because it's not contributing much to the second moment of area and Z values, whereas this is a bonus. So whatever you put here is a bonus, because that's the area that will be under higher stresses during the transfer and in service. Right? So those are bonuses, and this is a penalty. Right? This is a penalty. But we can't help it, because we have to cast it like that. So we have to face the penalty to a certain extent. Right? So now if you look at all these situations, today we stand a strong chance of going for 35-45 concrete for C35-45 concrete, 45 concrete for Prestressed. We have a strong chance of going for C35-45 concrete for Prestressed, right? So basically that's a situation, it's a practical situation. But you can see now, if you look at the price of cement at 500 rupees per kilogram. So let's look at this mix to see, how much it is going to cost. So we need about cement, sand, aggregate, and water, and wet density. So here you need about 500 kilograms, sand 720 kilograms, and aggregate 1080, and water 200 and 2500. So these are the numbers. Right? So if you look at the economies again, I'm just going deep into the things that we generally don't discuss, because these days we have to be very concerned about the cost. The reason is everything is very expensive. So unless we are concerned about the cost, it's very difficult to come up with viable construction projects. Right? If we just say, okay, I don't care about the cost of cement or whatever, it's not going to happen that way. So here we get 50 rupees per kilogram. And if you take sand, is about, so 3 cubes is about 100,000 rupees. 3 cubes is about 100,000 rupees, right? So if you look at 3 cubes means 3 into 3.28 meter cubes. So which means 10 meter cubes is about 90,000 rupees, right? And if you look at the density of sand, which is about 1,500 when it is loose, so we are going to get about 15,000 kilograms of sand. So if you look at 90,000 rupees, for 90,000 rupees, we are going to get about 15,000 kilograms of sand. So you can see the cost of sand is 6 rupees. And cost of aggregates can be little less, so we get about 4 rupees, and we'll forget about the cost of water. So you can see that the cost of the concrete is now dominated by cost of cement. So we see the cost figures, then we can get some idea. So we get 500 multiplied by 50. 25,000 rupees for cement alone. And then we get 720 multiplied by 6. So we get 4,320. And we get 1,080 multiplied by 4. We get 4,320. And water, we'll forget about that. And then the cost will be 25,000 plus 4,320 into 2. 33,640 for material law. So now we can see when you add the labor cost and all those things, we may be heading for something like 45,000 to 50,000 rupees per meter cube. So you can see it's a significant cost, right? It's a significant cost, and stuff cheap, it's a very significant cost. So that's where now we can think of how we can get a similar a good situation with this. So what we do is we go for cement, sand, aggregate, water, and wet density. Now what we do is we go for high grade superplasticization. We go for high grade superplasticization, right? So what we do is we go for high grade superplasticization, which is slightly more expensive, but it will allow us to maintain the water content at 130 kilograms. A drastic reduction in water content. So, and then if you look at the water cement ratio, let's say it drops to about 0.3, then we can get some idea about the cement content. So if water is 130, water cement ratio is about 0.3, and then cement is 130 divided by 0.3, you get 390. Now you can see, when you go for a very low amount of water, it will allow us to drastically reduce the cement content. And here again, we are not going for cement, we are going for cementitious material. So we can say we are going to use 325 cement and 100 fly ash. And then if you look at the numbers, because we are using about a significant amount of fly ash, we can expect the density to drop about 2,460 kilograms per meter. So density drops. So if you look at the numbers x and y, now you can see we are going to get x plus y as 2460 minus 325 minus 100. So we are going to end up with numbers like 2460 minus 325 minus 100. So we are going to get 2035, and x is equal to 2035 divided by 2.5. I'm going to take the same close to fine ratio, 814. Y is 2035 minus 814, 1221 kilograms. Right? So you can see now we are going to end up with 814 and 1221. Again, we can do something that is, generally we can add about 20% quarry dust. So 20% is about 160, we say 170, and 170, 840, 170, we get 644, and we can get chips 10 millimeter, 20 millimeter. So we get about 221, 500, 500. So the moment you do all these things, we are improving the mix. And then if you look at the cost, now the cost will be cement will be 325 multiplied by 50. Cement cost will be 16,250. And fly ash, let's say 15 rupees. 15 into 100, 1,500 rupees. And sand is 814 multiplied by 6 rupees. And that is 4,884. And the cost aggregate is 2,221 multiplied by 4, 4,884. Right? So if you look at this cost, now if you add those up, 16,250 plus 1,500 plus 4,884 multiplied by 2. So you get 27,518 as the cost. And you can see this is about 6,000 rupees saving per meter cube. This is about 6,000 rupee saving per meter cube. But we have to spend some money for aggregates. So, sorry, admixture. And admixture will cost something like 600 rupees, 700 rupees. So 700. So admixture might cost about 2,000 rupees. But still we will get a saving of about 4,000 rupees. So now you can see, this concrete technology is going to be very, very useful. And then what you have to do is you have to do a mix like this, and the strength development curve, which is going to go like this because it's going to rise, right? And so if you are going to do the trans at 4 days, we'll have to find the strength, and then you know, you can once you do the transfer, you can after a certain age, you can move it and even launch it and apply stresses. And when it comes to, but you know that this is going to go up, which is useful because you know it's going to be a very strong beam and very high durability with time to come, provided that you have done the curing function. So if you look at these numbers, now you can see we should not blindly do anything because in today's context in Sri Lanka, where material costs are very expensive, much more expensive than the labor costs, right? So I'm talking about relative terms, right? So labor costs are very much cheaper than the labor costs, material costs. And if I take an example from Australia, the Australia 1 hour of labor is $75 to $100 dollars, which is about 100 into 2, 75 into 210 is about 15,750 rupees to about 21,000. Whereas we can easily manage 4,000 to 4,500 rupees per day. So you can see, I mean, in the Sri Lankan context, this concrete technology and its optimization should be paid a lot of attention, because you know we can make a significant saving while ensuring what? While ensuring better durability, because when you have less water, it's more durable, better durability, and mix that is more workable, a flowing concrete, and then you know, a dense structure, and in the long run, super strong beam. And we know as the strength of the beam increases, even the tensile strength carrying capacity increases. So with all this, we achieve all this at a lower cost. And DEF, not possible. So you can see huge advantage. So always it's a must that we pay some attention to concrete technology on one side. Now the moment we look into this matter, now you can see we do not have to stop at this level. We went for 3545 because now we are using only 325 cement. Then you can ask, why not 4050 or C 50 60? So how are we going to achieve this? And so we see what could be the strategies available for us. Sorry. So I'll share the screen. So here you can see that we are talking about, we can talk about 40-50 or 50-60, and we know for sure that the stress range will be more, because now you can go for something like 2.9, whereas the elastic modulus is now 37, which means the deflection of the beam will be much lower. The deformation of the beam will be much lower. And up to now, this even 50-60, we can use all the normal equations that we generally use. But the challenge is on the side of concrete technology. So because we could reduce the cement content to about 325, now we see, I mean, how we face the challenge of much higher strengths, much higher strengths. So I'll stop here. Bandhu, is that clear?
Yes, sir. That is clear.
Right? Okay.
Yeah.
Right. So now we have to see how we can achieve even higher strengths, because now we can see now we are using only 325 cement, 325 cement. But I will tell the method, but I cannot give exact answer when you are going for super high strengths unless we do the testing. But I can certainly indicate the trend. So let's say we go for C50, 60 concrete. Now how are we going to deal with this? Right. So we have a transfer, service. So transfer, construction, and service. Because during the construction, we don't have loads, the same loads. So what we know is, because we may be using about 125 kilograms of fly ash, we know we are going to get a strength development curve that is going to go like that. So we can say here after 4 days transfer. So after about 21 days, you can release it for construction. After about 180 days only, we allow service. That means the bridge construction will take about 180 days to complete once the beams are cast. The moment we know this, we use this strength for calculating 0.6 FCU, but FCK, I'm referring to the corresponding value, not directly from this one, but we are looking at this 0.6 FCK. So we can actually use this value for that, and we can use this value for any construction, and we can use this value for transfer. Now, how do we achieve this condition? For this, what we do is, we first design a mix and then cast about 30 cubes. And then we do the testing at the age of 2 days, 3 days, 4 days, 7 days, then 14 days, 21 days, 28 days, something like 56 days, 90 days, and 120 days, 150 days, and 180 days, and then we go for testing about 365 days, and so we just keep the cubes, sufficient cubes, so that we can have 2 years as well. and we develop a curve. The idea of developing a curve is once the curve is developed, if you are consistent with the type of cement, then we can actually go for, if you are consistent with the type of cement, so some actually go for one particular brand of cement. Then what happens is, we can, once we develop these curves, we have a reasonable idea. So you will get all these points on it. And once we develop this curve, we can go for such a situation. And now we are looking at C50-60 concrete, fairly strong concrete, C50-60 concrete. So the method is you have to develop a concrete strength development curve by testing how many cubes. So if you are going to test about 3 cubes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 into 3. So you have to cast about 28, about 40 cubes. And then develop a strength development curve. And once you know the strength development curve, you can have small margin for safety. So the actual curve that you use is something like this. So you can keep a margin of about 8. You can keep a margin of 8 here from this one, and you can select the strengths. Right? So if you are going for something like C60, that is 60 megapascal concrete, cement, sand, aggregates, water, and then you get with density. And we can try cement like, now we want something like 60 megapascal. So it may be a good idea to go for about 450 cement. Now you can see it's a significant increase, and about 125. And still the water will be about 130 or 130. 130 divided by 450. We can see, because there's a minimum we can go 130 divided by 450 is about point, no, 450. So this is 130 divided by 450 plus 125, 575. So water cement ratio is 0.226, right? That is quite possible because the minimum is 0.23, so we have come pretty close to the minimum. And then the density also will reduce to about 2,400, maybe 2,460 might still be a valid number. So if you look at these numbers, now you get 2,460 minus 450 minus 125 minus 130, and that is 2,460 minus 450 minus 125 minus 130. You get 1755 divided by 2.5. You get 702 and 1053. Right, 1053. And again, if you look at the cost, now the cost will be higher, but still it will be less than what we originally got without using aggregates, without using admixtures and fly ash additives. So we originally got a cost of something like 33,640, and the cost of this one also will be pretty close to that value or slightly more. But now you can see we are going for C40, C50, 60 concrete, So 50 multiplied by 0.6 is what we are targeting, and 50 multiplied by 0.6 is 30. 30 and the 30 plus again another 2.9. So you get about 32.9 megapascal stress range. A huge stress range, but cost-wise, you are still at a lower level. But how we achieve this is by going for trial mixers. Once you go for a logical mix, because these strengths are very high, but so you have to go for a very low water content to achieve it, because the only way you can achieve it is by using uh, this kind of very high grade super plasticizers, and they are actually manufactured in Sri Lanka by Mr. Ravi Nissanka. He's the only guy who is manufacturing, I think, this particular product. You can check the market, but Mr. Ravi Nissanka, and his number is Note 71248 1484. 71248 1481. So you can take down the number, and you can talk to him, and he has a huge knowledge on this kind of construction, and you can actually learn how this can be done, because I have explained the background to you. So if you can actually go to this level of sophistication, then we can actually go for very economical displays. Then you will ask, has it already been done? The answer is yes. When you go towards Navamavata, and when you go towards Slave Island railway station, there's one project that has been stopped for the time being, and those beams are actually designed for this kind of very high strength. The reason was there was a huge restriction on the height of the beam. Because of that reason, uh, the design engineer had to go for very high strength concrete, and they actually achieved the design targets by using extremely high strength concrete. And then when it came to the concrete technology, that part was also handled separately. So you can see Eurocode allow us to think loud and go for very economical designs, because when you see the strength range, as we increase the strength, range increases drastically, and when the strength increases, strength range increases drastically along with the stiffness, that is the elastic modulus, we can actually optimize the beams to a great extent. So that's the kind of logic that we are working on. Is that clear?
That's clear, sir.
All right, good. So what we like is, our engineers adopting this kind of sophistication rather than, going with the conventional designs, because, conventional, why we have gone is, when you go for a conventional design, you feel you are happy, because, you are just doing what the others have done already. But this type of designs will be considered as cutting edge. And if you don't do this, the moment you do a design, somebody else will come and do a value engineering, and your design will be out. So it's always better as the design engineers to try these things. And also, you have to be very reasonable with this number, right? At which day you are going to do the stressing operation. That is, either you apply the stress or cut the tendons. So this age at which you do the transfer is also important. But you can see these stresses are, although we are going for a very high target here, this need not be very high. Why? Because we have only the self weight of the beam. If we have only the self weight of the beam, I mean, you have to introduce an additional construct level of calculation, and that is this. That is the construction stage. What is going to happen to the beam during construction and immediately after construction? Because that's also important, because just when you place the beam, it will not end there. You might add a little bit of additional concrete and load it, but you are definitely you are not going to get the HA and HB type vehicles, or the normal and special type of vehicles. You are not going to get it. So for that, you can have a different change, where as long as you are sure that the concrete is going to gain strength. And how we ensure that concrete is going to gain strength is by using fly ash as an additive, because we know if we cure the concrete properly in the first few days and generate sufficient calcium hydroxide as the byproduct, definitely concrete is going to gain strength over a longer period, because fly ash is going to start a secondary reaction with this calcium hydroxide and generate more and more gel. And when with more and more concrete gel, you will get higher strength. And finally you can achieve your target. So that's the way we have to look at the use of high strength concrete. And if you say I'm going to achieve 60 megapascal in 28 days, it's totally unnecessary. Rather than doing that, you can easily introduce an extra calculation layer, that is the calculation stage, and that is during construction. What's going to happen during construction? So this is the construction stage. So you are going to say what is going to happen during construction. As long as the beam is strong enough to withstand the stresses at the construction stage. Only thing is, when you have to again use the correct E value applicable to that strength range. That way you can easily work out the stress history for the pre-stressed beam that you are designing. And with the stress history that you expect, we can take, we can optimize the designs to a great extent, right? So that's the way you have to look at it. So that is the concrete strength, the concrete technology part. And so now I can move to the next layer. That is, how do we look at the section? And so if you look at what actually happens, again, we can proudly say that, in Sri Lanka, because of the pioneering work of, very brave and talented engineers like Dr. N.S. Kulasinghe. I mean, we had these technologies in Sri Lanka about 50 years ago. And those days, they actually went for a very simple bridge beam, which is only about, it has a small, very shape like this. And you place it side by side. So this has a span of 6 meters or 20 feet. It's a small bridge, but it's big. And you don't have to do anything. What you do is you put a tie rod here and tie all these beams. Put a tie rod, tie all these beams. So you get a lot more beams, because these are small beams. But you see now, this is not economical at all, as far as pre-stressed concrete is concerned. But because these depths are so small, you cannot create an I-beam either. They thought, okay, this is a very rapid construction. And what you do is, after that, you can put a small street here, just a street with some little reinforcement. And next day, the bridge is ready for use. Right? And then you'll ask, okay, now, This is only for rapid construction of the deck. So you need to have 2 apartments. So what are you going to do with the apartments? So they had no fear. I mean, they thought, okay, now this is going to be simply supported. And you might have a rubber pad here. It's just simply supported. So as long as you have you can create some strong material here that will resist the scouring. There's no problem even if it tilts a little bit. No problem. Why? They simply supported. These are simply supported. Nothing will happen to the bridge. Nothing will happen to the bridge. So they did not. They went for this kind of simple solutions, and they never tried to have fine foundations. What you do is, if you are not sure of the foundation material, bring a large JCB, excavate a big pit, remove all the loose materials, and compact and refill it with something like ABC. And to make sure that if you think that covering potential is very high, then what you do is you add about 8 to 10% cement to this ABC and fill it up. Then the fill will also have strength, and you will find that the bridge can be constructed very fast. So, but our experience is, even for a small bridge, people take a lot of time. But but if you look at this type of approach, you'll see that it's not there's no need to have a huge duration to construct a bridge. It can be done pretty fast, right? So here again, you can have these opportunities for drainage. And also, in addition to that, some of these also can be precast. It can be precast with some opening for the dowel bars, so that once you stack them all, you can actually use the dowels and fix all these pieces. And then another very popular bridge is that you will place the beam like this, and this can be even mass concrete. And when the foundation is firm, what you do is you will pour concrete with some reinforcement, and this is called integral bridge. Integral bridge. That means you fix it, and then you'll ask our thermal expansion. But that is not a problem for Sri Lanka at all. Why? Because our temperature range is very small, about 6 to 10 degrees, very small. So with such a small temperature variation for 20 meter span, nothing can go wrong. So you don't waste your time or anything, just connect everything and concrete it and complete the bridge very fast. Because it's all connected, after 2-3 days, you'll find now the slow moving traffic can be allowed on the bridge. Slow moving traffic can be allowed on the bridge. So this is one of the first shapes that they used for prestressed concrete beams, and they were precast beams for small bridges up to 6 meters. They use this particular type of bridge beam, which is precast and constructed with long line method. So what is long line method is, we create some abutments And these apartments have to be properly constructed. So you have to bury steel sections and create the apartments. And then we have very long line of pre-stressing here, stress, and then we cast beams around it. So that is a long line method. Which is used for pre-tension beams. So again, you can think of very high strength concrete, because that's one way of actually overcoming the current very high prices for construction materials. So, currently we have very high, extremely high prices for construction materials. So how we overcome that? This is by going for long line method. But again, in the long line method, we'll be little careful when we write the specification, because now let's say you write a specification which says after 1 day, after 24 hours. Sometimes you might specify after 3 days or 4 days. So don't write a specification unless you are sure that whatever the strength specified can be obtained. So somebody says 20 megapascal in 24 hours, and you can achieve it, but not easy, right? On the other hand, somebody might say 25 megapascal after 3 to 4 days might be quite possible, right? So, or might say 30 megapascal after 4 days, something like that. It's quite possible to achieve. But when you say 10 in 24 hours, that means there's something wrong with your, concrete knowledge, because if you look at cement, and as you have seen here, cement consists of what? This. After 24 hours, you get the strength from with this. And if you ask for a huge strength, then you are asking the manufacturer the manufacturer of the beam to select a concrete with higher tricalcium aluminate content, which is detriment. So if you are asking for very high strength in the specification as a consultant, always get some idea about the concrete technology and go for some reasonable values. And especially the most important thing is, if you want extremely high strengths, very early stage, you must go for steam curing. And when you are doing steam curing also, you have to maintain the temperature of the steam, the components around 65 degrees by controlling the steam supply. The reason is, if this increase goes beyond 70 degrees, then you might get DEF, deleterious light formation, if the temperature is more than 60. So we actually, once we were involved in a project, a new product, which is the round pole for Sri Lanka Telecom, SLT, and we had to achieve something like 65 megapascal in 24 hours. So we did not try to do something impossible. We simply went with steam curing. And after 24 hours, we achieved 65 megapascal. So in Sri Lanka, using the locally manufactured cement, as far as I can remember, or cement that we got from neighboring countries. We did not go for a very special product of cement. So basically, many things are possible. And so you have to understand the theory properly so that you can optimize. But also as consultants, always keep in mind that you should be reasonable with the construction team. So, for example, when I was in Australia in 2003, and I was teaching PT for the students of Queensland University of Technology for bridge engineering. And so we went for a site visit for the manufacturing yard. So they were using 40 megapascal cylinder strength as for the Australian practice. And this guy said, somebody has said at service 40, at transit 40. And you are saying, okay, now can you imagine that there are engineers who specify the same thing for these, because these are going to happen in two different ages. So we have to be always concerned. And also, especially if you are a consultant to a project, you have to be extremely careful because you are going to get a lot of problems. You are going to create a lot of problems to the casting yard unless you have a good understanding of the concrete technology. So, and especially it's good to get some information about the strength development curve from a specialist like Mr. Ravin Sanko, because he has done so much testing and development. He has developed so many curves. So if you are a consultant, always get some advice from a person like that. Otherwise, you yourself might have to go for some casting of cubes with possible mixers. And if you do that, you stand a chance of hugely reducing the cost of construction. So that's how it is, not just the normal optimization that is possible with prestressed concrete, but this is taking it one step further and making it as low as possible or the best optimum solutions. Right? So that's what we can find. Right? So then we all know that when we use prestressed concrete, what happens? We have steel that will take a shape like this, and this is 1860 megapascal level, and we go for something like 70% of that. 70% of that. .7 into 1860. So you get 1302 megapascal. And after this, what happens? We get part of this loss due to elastic shortening of the beam. Then another part will be lost due to shrinkage. Another will be lost due to creep of concrete. Another part will be lost due to relaxation of steel. So you can see, after all these losses, we are going to end up with something like 932, 950 megapascal as the stress in the steel. And then what happens? So So now this is the service condition, and under the service condition, this can be subject to ultimate loads. Ultimate loads. So all this time we were talking about service conditions. So we have a cable. Now it is the curve. Now it has come down to 930, and it will fail at 1860. So what will happen now? So you can see we start with a beam like this. Then it has to become horizontal, and then it has to do that. Whereas in reinforced concrete, we start from here and we go until this. So this is the difference between prestressed concrete and so here what happens? So here is in compression, this is in tension. So this is the steel in compression. So from here to here, you get this stress range. And from that one, it will go on stretching like this. Right? So it will keep on stretching like this. Whereas in reinforced concrete, it's just a normal stress strain curve, and you look at the relationship. But here we start at in a situation where at the level of the tendon, the beam has already shortened, and because of that reason, first you have to make it horizontal, then you have to take it in the other direction, right? So because of this reason, now we will see there will be a certain strain and another stress until it comes to this. So this is A, this is B, this is A, this is B. And if we can show that, then what happens? At the ultimate state, beams will crack. Because now you can see the strengths are very high, very high. So beam will crack. And that is okay. Why? Because with these cracks, prestressed beam will start giving us warning. It will start giving us warning. So because it's going to go on give us warning, we have no problem, because it's cracking and warning us that it's too loaded too much and get away from this place. But the beauty of prestressed concrete is, if the concrete does not crush, the moment you remove these loads, what will happen? The beam will bounce back and close all the cracks. So that is one of the huge advantages of prestressed concrete. So that's why we say, now here you can see we are in a particularly advantageous position when it comes to ultimate loads, because unlike in reinforced concrete, we have a huge strain range for this steel, because this is high strain steel. The elastic modulus is the same. So because of that reason, we will end up with a huge advantage in this particular situation. And because of that reason, these beams generally do not fail in ultimate loads easily. And if they ever have, it could be a service condition. But if you have properly designed the beam on the surface, automatically, most of the time, you will find that the ultimate loads can be easily taken by prestressed concrete beams. And the beauty is, the moment, unless you load it to a very high level, if the concrete has not crushed under the stresses, very fast, the moment the load is removed, the prestressed concrete can bounce back. And I can give you a very good example that we encountered some time ago in 2009. And this is civil engineering. number 6, 7, 5, 6, 7, 7, 8. This is 9. So this actually happened in 2009. There was a bomb attack, plane attack on Colombo, and the plane was shot at this place. So the engine went into the Inland Revenue Department building. So it started burning. The blast occurred here, and there was a prestressed concrete slab constructed using prestressed concrete beams. So the beams are of this shape. As far as I can remember, I think they were double T's, or it could be a single T, but as far as I can remember, it was a double T or single T like this. So what happened was, the blast was so high, they went into ultimate. But because this top flange is so wide, concrete did not crush. It could be that concrete has gained strength as well. So we had some cracks in the beam, but beam recovered fully, and then we did not have to. We just did some strengthening because we had to look at the durability. The reason is the moment the beam is cracked and some steel has yielded, then you have to always look at the durability problem. But as far as service loads were concerned, we did not have a major problem. So you can see the same advantage can be gained in all the types of beams that we use for prestressed concrete. And so because this particular section is so inefficient, and so then people thought, okay, let's go for this section. And then they thought, okay, so we have now the deck. Let's feed it with concrete. But if the load is too much, put some void form and this is called inverted T. So what happens when you are doing all these calculations under transfer and all these conditions, building as a height H1, and then when it is subject to ultimate, then you have a height H2, and still who carries the load? This beam is carrying the load. But what has happened now? Earlier, the centroid is here, close to the bottom flange, say Y2, and now it will go up and you get Y2 dash. And with that, you will have to see how we can design this improved version, and these are called inverted T type beams. So we are going to look into the equations of this particular situation next time. Only thing is, because of the New Year vacation, because many of the participants may be pretty busy during the New Year season. What we thought was not to have 2 lectures, in the consecutive Tuesdays. And to start today's 4th plus 21, 25th. Is that right?
Yes, sir. 11th and
So
18th, we are not going to have the lecture. And
18th, yeah, 18th.
Yeah.
18th April, we are going to have the lecture.
No, sir. We
No.
plan to skip 11th and 18th as well.
Yeah, 11th and 18th, we don't have the lectures. That is not there.
25th,
and 25th.
Yes.
Yeah. So on 25th onwards, I will explain how to go for this. This is called composite. This is called composite. Because we have laid concrete that was cast later. But that is also contributing to carry the load. So this is called composite construction. So we'll talk more about composite construction from 25th onwards. And after that, with that, I will also gradually move on to introducing the structural analysis part using SAP 2000 as an example. But you can also use MIDAS and in the CESC bridge, and they have more sophisticated facilities for generating the bending moments and shear forces automatically. But I will not use any of those facilities. I will show you how to think about it. Because, the most important thing these days is because we have software, software can actually solve the problems very easily. But at the same time, we should know how the software works before using the software. So for that, it's good to know, do some exercises manually. And then when we can handle situations manually, you can always use the software with a greater degree of confidence. So we are going to look at it in that context. So we'll talk about composite, but today I thought I should touch on the construction aspect before we go deeper and deeper into the design aspect, because in prestressed concrete, it's very important to take correct decisions with respect to the strength of the material, that is strength of the concrete, and on the other hand, we also should be very much mindful about minimizing the amount of steel needed. And for that, you have to always understand that manual diagram can actually come to our rescue, because it clearly tells at the most critical section where we should be selecting the pre-stress that we are going to apply. So that's why this diagram is so important, because we must always try to stay as close as possible to the minimal pre-stressing force, right? Because any other pre-stressing force will be higher, but that will also satisfy all the stress conditions. But we must always keep in mind minimum pre-stress is the minimum. So shall I end the lecture with that note?
Yes, that's fine, sir.
Right.
And one question, sir.
Yeah.
Can we achieve a complete crack recovery as mentioned? I mean, 100% crack recovery from that rate?
Yes. Provided concrete does not crush, right? And then if you want a real recovery, then the ideal is going for unbonded tendons. Unbonded tendon, because when the tendons are bonded, if the loads are extremely high, if the steel yields, then you can't have 100% recovery, right? But on the other hand, if it is unbonded tendon, then at every section, what you get is an average stress, not a concentrated stress, right? So in that situation, always you will get finite recovery fully, because steel has not stressed, provided concrete has not crushed. So that's why this concrete technology, and also using fly ash and allowing it to gain strength over a longer period of time, all that is very, very useful, especially in the over stressed conditions. Have I answered it adequately?
Yeah. Yes, sir.
Right. Any other question? I think chat has something. You can ask anything. Okay. 100% practical. Yes. Okay. That's a question that you. Okay. Right.
That's all it seems, sir.
Yeah. Okay then.
Yeah.
Then shall we? We'll end here. Okay.
Yeah. I would like to invite Engineer Bashita to do the vote of thanks.
Dear all, I am pleased to deliver this vote of thanks for the 7th session of the webinar series on structural design of highway bridges conducted by Professor Tishan Jayasinghe. On behalf of the organizing committee, I would like to express our heartfelt gratitude to Professor Tishan Jayasinghe for his insightful and informative presentation. The webinar series has been a great success, and we have received numerous positive feedback from the participants. This would not have been possible without the support of the CESC chairman, engineer Mrs. Kamala Gunawardana, the IESL secretariat, the publicity department, and the IT team. We would like to thank them for their dedication and hard work in making this event a success. We would also like to express our appreciation to all the participants for their active participation and insightful questions. Your enthusiasm and engagement have made this webinar series a valuable learning experience for all. Finally, we would like to inform you that the next session of the webinar series will be on 25th of April. We hope to see you all there. Thank you. Thank you very much.
Okay, thank you very much then. Thank you.
Thank you. Thank you, sir.
Thank you.
Okay, sir. Thank you, sir.